So I'm Jeree. I worked in the CCQ this summer on spin and charge phases and TMD heterostructures. So a heterostructure is made by stacking 2D materials on top of each other. So 2D materials, if you think about like a typical solid, it's made up of multiple atomic layers. So if you were to peel back the atomic layers of a solid until you were left with one, that would result in a 2D material. And you can stack these materials on top of each other, and what emerges is a lattice mismatch, which creates a moire potential. So the specific model that we're studying is made up of a heterobilayer, meaning that we're using two different 2D materials. So because the materials are different, they naturally have a different lattice structure, which results in a lattice mismatch, which gives rise to the moire potential. And the mismatch is shown in the red picture. It's a pattern that repeats itself periodically. So this is the model that we're studying. So the moire potential is the last term. So V sub m represents the depth of the moire potential, and inside of it, the shape parameter phi controls the shape of the moire potential, and that's pictured below. You can see how changing phi affects the shape of the potential. So the first term in the Hamiltonian represents the kinetic energy. So W is the bandwidth, which represents the kinetic energy scale. And then the middle term is the interaction energy, and U represents the interaction energy scale. So we can divide the bandwidth, which is the kinetic energy scale, by the interaction energy scale to give us the mean interparticle distance, which is denoted by R sub S. So this is inversely proportional to the electron density, because as you increase their distance, you are decreasing the density. So in choosing which moire potentials we want to run calculations at, we wanted to ensure that the moire potential would have an effect. So in order for it to have an effect, it has to overcome the kinetic energy. So this ratio here, V sub m over W, has to be of the order of 1 because we want the moire potential to exceed the kinetic energy. And so we're studying the stability of different magnetic phases as a function of this shape parameter phi. So this is what we'll be changing. And so within the interaction energy, it's made up of all of the electron-electron interactions. So we can break this down conceptually into three parts. There's the Hartree energy, the exchange energy, which arises due to the fact that electrons are indistinguishable, and then the correlation energy, which arises from each of the electron-electron interactions. But in a system like this, there are so many electron-electron interactions that it's really difficult to calculate correlation energy. So this is why we use density functional theory. It lets us approximate the correlation energy as a function of electron density, which is something that we can calculate. And the specific approximation that we're using is shown, which is the local density approximation. So we're studying three different magnetic phases. The first one, which is the paramagnetic phase, it's not pictured here, but it's the phase that corresponds to no magnetism. So for every upspin, there's a corresponding downspin, so all of the spins cancel. And there's no net spin, thus no magnetism. The second phase is the stripe phase. As you can see, it has a row of upspins and a row of downspins forming a stripe pattern. And then the third phase is the 120-degree phase, where the electron spins point in all directions of the plane and they form 120-degree angles between each other. So this first plot, the y-axis is showing the energy of these two magnetic phases relative to the paramagnetic phase because we're looking for the least energy state. And then the x-axis is the Vm over W, which I spoke about earlier, to ensure that we're running the calculations at moire potentials where we'd expect to see an effect. So the green vertical line shows the point where the 120-degree phase slips below the paramagnetic and the stripe phase, and it becomes the least energy state. Now, although we know which state is stable here, we want to be able to further characterize what type of state it is. So this is why we're able to plot the band gap. So the band gap is defined as the minimum amount of energy required to excite a state. So when there's no band gap, it's easy for electrons to move, and we characterize it as a metal. And when the band gap is non-zero, it acts as an insulator. So on the left in green, we're plotting the magnetization, and on the right in purple, we're plotting the band gap. So the first phase before the green vertical line is the phase where there's no magnetism and there's no band gap, which corresponds to the paramagnetic phase. And in the middle, although the magnetization has jumped, there still remains no band gap. So now we have a 120-degree metal. And then the third phase, after the vertical purple line, the band gap has opened up and we still have magnetism. So we have a magnetic insulator. So we repeated these calculations at 3 different shape parameters, 0 degrees, 26 degrees, and 60 degrees. The red represents the paramagnetic phase, which has no magnetism and no band gap, which is just a metal. And the light green represents the 120-degree phase, where the band gap is still at 0. So we have a 120-degree metal. The dark green represents the phase where the band gap is opened up and the 120-degree phase is stable. And so we found that as we increase the shape parameter phi, the paramagnetic phase expands itself as the stable phase. At phi equals 60 degrees was the only phase where we found the stripe phase is energetically competitive. And the phases where there's magnetism but no band gap, the magnetic metal phases, which are denoted in light green, tend to happen right in the middle when the Moiré potential is neither too strong nor too weak. And I should note that the shape parameter in our model is determined by, so I said that the heterobilayer is formed by stacking 2 different 2D materials on top of each other. So it's innate to the choice of materials that you use. So whichever 2 you choose, it corresponds to a specific shape parameter. So for future projects, expanding these phase diagrams both up, which would be at higher Moiré potentials, and outward, which would be at higher, lower electron densities, but higher RS values. And then just more exploration of those phases in the middle where there's magnetism, but there's no band gap.
All right. In the room, are there any questions for Jeree? So I was wondering, you're talking about these 2D metals, and you were actually talking about looking at 2 different metals that were laid on top of each other, or 2 different materials, not metals. The 2D material that I've heard the most about is graphene. So I was wondering, would your models work with graphene or like, I guess, sorry, let me step back. Could you tell me some example materials that you might be talking about when looking at this?
I know a popular one is MOS2 right now, but the difference between, so like the model that we're studying, the heterobilayer, where there's 2 different materials, graphene is made up, so it's the same material stacked on top of each other, and so to actually have the Moiré potential emerge in that model, what you have to do is you stack them and then you have to twist them to a specific angle to create the lattice mismatch. So this is like an easier way to have that Moiré potential emerge. In this case, you don't have to twist them, and you can just use different materials so that there will be like a natural lattice mismatch. But I also know, like, what makes it hard with graphene is that the Moiré patterns only emerge at specific angles. Like, I think one of the experiments, it was specifically at 1 degree, and so it makes it really hard to like fine tune it to that. So this is like an easier way to do that. But the 26-degree phi parameter corresponds to a specific experimental setup. I don't recall exactly which materials they used, but the other 2, I don't believe there's an experiment corresponding to them right now, so I'm not sure which materials they are, but they represent different materials. Okay.
And what about when you look at the Moiré patterns for 2 different materials like you're studying, are they periodic? Like this pattern, does it repeat in some number of like lattice sites or something?
Yes, so they repeat like out to infinity, and that's actually how we simulate our unit cell. So you can see like these right here are the different patterns that emerge, and then those three patterns just continue to repeat as you go out. So we only actually create that one unit cell, and then that's what kind of the computer repeats to
Okay.
simulate it.
Great. Cool. Are there any questions on Zoom? Okay, so let's thank Jeree again.